So far in the chapter, we've seen how to add one OH across the alkene. And now in this video, we're going to learn how to add two alcohols, and that process is called dihydroxylation. In the dihydroxylation, we start with a double bond, and what we do is that we will add one OH on each side of that alkene. There are two types of dihydroxylation. The first one is the syn type of dihydroxylation, and we call it syn because both OHs will end up in the same side of the molecule. To get a syn dihydroxylation, we will often use osmium tetroxide. You don't have to memorize the mechanism, but it's really helpful to remember this molecule to see how, you see, it chelates. It approaches the alkene from the same side, and that's how we end up with the two OHs from the same direction, because they come from the same molecule, from the same osmium tetroxide. Because of that, when we treat the double bond with osmium tetroxide, we get this ester right here that then is reduced to the alcohols. So you will always see two steps. You will see osmium tetroxide, and then you will see either one of these two that will, what it will do, it will cleave this osmium from the oxygen, and that's how we get the diol. Osmium tetroxide is very expensive and it's very toxic, so we try not to use a lot of it in the lab. And so chemists have come with ideas to reuse the osmium tetroxide and just use it in very small amounts that can be regenerated in the reaction. So one of them is using osmium tetroxide with this molecule right here, NMO, and the other one is using osmium tetroxide with peroxides. And so don't be surprised if you often see osmium tetroxide with some additives like this one. Just be aware that those are to regenerate the osmium tetroxide and to be able to use it as a catalyst. So for example, when we have this molecule right here, you see it's treated with osmium tetroxide, and then we have the second step that will be the quenching and breaking that osmium oxygen bond. So what we will get when we treat this alkene with osmium tetroxide is both OHs from the same side. And don't forget, sorry, that we have that methyl that it's still there, right? So we end up with the two OHs on the same side. Remember that the two OHs can either come from the top, the two of them, or they could both come from below. So we can also get this molecule right here, which is the equivalent, right? So either the osmium tetroxide attacks the alkene from top, giving us the two OHs as wedges, or it attacks it from below, giving us the two OHs as dashes. Another way of getting syn dihydroxylation is with potassium permanganate. So you see the mechanism is very similar as osmium tetroxide. It's just that we don't isolate this ester that we were seeing in the case of osmium tetroxide. The potassium permanganate is more reactive, and we get the same type of reaction. So we get a syn addition of two alcohols across the double bond. That's all you need to remember. In the previous video, in the one where I was talking about epoxide opening, I kind of hinted at how we can get a dihydroxylation, but that it's anti. If we start with an alkene and we use MCPBA or any other type of peroxides, right? Peroxy acid, sorry. MCPBA is a peroxy acid that will give us an epoxide like that. And when we treat an epoxide with acid, what will happen is that first it will get protonated, and then the water can come and attack from the opposite side, opening the epoxide, and that's how we get a diol where the two OHs are in opposite sides. That means that it's trans. And here, see that it says NEN, that means enantiomer, which means that the water could either come and attack from this carbon right here, or it can also attack this one right here, and we will get the opposite, which is one alcohol down and one alcohol up. And here we have the mechanism again. So starting with the alkene, we form the epoxide, and then the epoxide gets protonated. Now the water will come and attack as a nucleophile, opening up that epoxide. So the OH that is coming from the epoxide will end up here on top, and the water will stay here at the bottom. Now a second molecule of water is going to come and deprotonate it, and so that's how we get two alcohols that are on opposite sides of the alkene, or where the alkene was originally.